Now we're moving into current events, looking at ocean currents. So let's find the right PowerPoint here and get it started. There we go. A current specifically refers to water moving horizontally. If water is moving up, that is upwelling. Typically, deep water is cold and higher in nutrients because stuff living at the surface has died, sunk down, decayed. And so upwelled water is typically cold and relatively rich in nutrients. Downwelling is water from the surface sinking deeper. Not surprisingly, that will tend to bring water that is warmer and also more nutrient poor deeper down. As we'll see, different parts of the ocean characteristically have these different patterns of water movement. One driver of differences in movement in water or air is differences in density. Air, aren't we still talking about oceanography? Well, yes, but as we'll see, the winds are main immediate cause of currents on the surface of the ocean. So we need to look a little bit at how the winds behave in order to understand how the ocean currents behave. And of course, we'll look more at winds as we move on to meteorology. Okay, differences in density in the air. Well, no surprise, temperature. You're probably acquainted with the fact that hot air balloons go up. Hot air going up, okay, density going with temperature. Pressure. As a gas, air can do quite a lot of getting more squished or expanded. And so we have variation in pressure that gives difference in density there. One area that's different from the pattern that we see for the oceans, air density is influenced by how much moisture, how much water vapor is present. No, salinity is not a very important factor in the air. Of course, seawater, well, it is water. So moisture content isn't exactly a big factor, but different amounts of salt are important for the seawater. For the air, different amounts of water vapor. So again, warm air is less dense than cold air, and moist, humid air is less dense than dry air. An area of low pressure then will be a place where we've got warm air and or humid air. Air will move away from places where there's higher pressure to lower pressure. Not a bad thing to do if you can move away from high pressure. So low pressure areas where air is moving up. A vacuum cleaner produces low pressure, for example. High pressure, well, that suggests our air is colder and or drier. And so in the area of high pressure, air is moving down, and well, it can only go down so far. It will then move out to the side and away as it reaches the ground. In high-low pressure, for air, we are typically thinking of what we experience living on the ground. So high pressure will mean that that air is sinking down, pushing more on us. Low pressure means that air is rising up and pushing down on us less. Now, of course, if the air is rising up from here, there's probably somewhere up there where the pressure is higher. But we're mostly focused on the pressure down low. There'll be a couple points in meteorology where we'll get to higher up pressure. If we've got area of high pressure sinking air somewhere and someplace else of low pressure, well, that sinking air hits the ground, goes sideways, goes up. And so we'll typically see flow from a high pressure area to a low pressure. This is true in water, air, anything really. Even the slow flow going on in the mantle will show that pattern. So this sideways flow, again, water, it's a current. In air, that's a wind. Not surprisingly, if we have a bigger difference in pressure between our two spots, or if they're closer together, then we get stronger currents or winds. If they are farther apart, if they are weaker, then we'll get correspondingly weaker flow. So our winds, one thing about wind, the tradition is naming them based on the direction that they are coming from. So for example, for us being in the northern hemisphere, a north wind is coming from the direction of the pole, and a south wind is coming from the direction of the equator. So north winds this time of year feel pretty nice. Come February, we generally just as soon have a south wind. Somewhat confusingly, ocean currents, if they are named based on direction, it's the direction they're going, not the direction that they're coming from. Yeah, it's tradition, we're stuck with it, but it is confusing. Fortunately, ocean currents aren't as commonly named with regard to direction. Now, of course, you probably noticed winds sometimes blow various ways, but there is a long-term typical pattern for most parts of the world where winds are usually blowing in a particular direction. And so this global typical pattern of winds goes back, not surprisingly, to the sun, our main source of energy for the air and for the oceans. Different parts of the Earth's surface get more or less heat from the sunshine, and that sets up differences that lead to wind patterns. Of course, near the equator is getting the most heat, most energy from the sunshine because the sun's shining straight down on it at least part of the day year-round. Places near the poles, the sun is always pretty low in the sky, and so they get less energy there. So this will tend to set up warm air at the equator. Warm air expands, less dense, rises. Around the poles, colder, denser, sinks. So this will tend to, oops, wrong button, set up a loop with rising air. If you can see the mouse, hopefully you can, near the equator, then traveling towards the poles, sinking down near the poles and back again. Nice simple model, which probably means that it's not too accurate. Real world is complicated. In particular, this ignores, remember from the first lab, the way that things spiral when you're on something spinning, such as the Earth. And so we have to deal with the Coriolis deflection. The deflection specifically is the amount that's bending. Coriolis effect is a general term for the whole phenomenon. Here in the northern hemisphere, we're north of the equator, and so things end up bending towards the right of how they would otherwise go if there weren't spin affecting them. In the southern hemisphere, things tend to bend to the left. Basically, the problem is the Earth is not holding still as the object is moving over it. Earth is so big, we don't feel the spin from it, but we can appreciate this sort of thing, say, with a merry-go-round or other smaller rotating object. If you were in a position like here with the blue horse, trying to throw a ball to your friend on the red horse, if you threw towards where they were to start with, by the time the ball gets there, the horses move forward and the ball will be behind. So this is what somebody not writing could see was happening there. But from the point of view of the folks writing, it looks like the ball has been backwards from throwing it. We're writing on the earth, and so things seem to bend. Yeah, it's really us writing the earth, but it's more convenient to think of the bending from our normal point of view. Here's an example of the importance of thinking about this. If a pilot was supposed to be flying a plane from Stockholm in Sweden into Lagos, Nigeria, and ignored the Coriolis effect, then would end up instead in Brazil. Passengers probably wouldn't be too happy about this. This is because while the plane is flying south, the Earth is turning under the plane. And so from the point of view of us standing on the Earth, the plane appears to go off sideways from where it should be going. The size of this effect depends on where you are. At the equator, you have to go all the way around in 24 hours. At the pole, all you have to do is turn around. You're not making a loop at all there. So at different points on the Earth's surface, you're getting different degrees of impact from this. Excuse me. Among other things, this leads to why you want to put your rocket launch site as close to the equator as is practical. For example, in the US, we've got the base at Cape Canaveral as the main spot for NASA launching things. Soviet Union didn't get that far south, but they stuck things in Central Asia as far south as they got. European Union has their launch base in French Guiana, northern South America. Why? Well, your rocket, by being right at the equator, is riding the Earth at about 1,600 kilometers an hour. Trying to launch from some place like southern Alaska, and it's got only half that speed. So having the greater speed of rotation helps the rocket have a faster speed in its travel. Okay, what does this do to the winds? Turns out that instead of a single big loop going up, rising warm air at the equator and sinking at the poles, we characteristically get a 3-loop pattern in either direction. So 3 loops going north, 3 loops going south from the equator to the pole. This pattern then sets up winds in different directions, as the picture here is illustrating. So we've got one loop that's roughly equator to 30 degrees north or south, one from about 30 to 60 north and south, and one between 60 and 90. Now, roughly, winds do move. After all, we're just talking about air. It's not hard to move air around. So these are not going to be perfectly fixed in place all the time. Different weather systems can disrupt it. Also, more long-term, you have things like the seasons. Northern Hemisphere summer, the warmest zone moves a little further north. Northern Hemisphere winter, southern summer, that warm zone moves a little south, so you're going to get these boundaries moving around some. It's not like this all the time, but say, like if you pay much attention to weather patterns, you're probably aware that if a storm is hammering Atlanta, we'd better pay attention. We're next. Typical wind directions are fairly consistent. Now, any one day, weather could change. We can have wind going all sorts of directions. But more often than not, our winds are coming from the west-southwest. So we have this variation in wind patterns depending on where you are. And this in turn will be a major driver of the big current patterns in the oceans. Overall, the result is that winds that, if the Earth weren't spinning, would be blowing towards the equator, get bent off to the west. Winds that would otherwise be blowing away from the equator get bent off towards the east. Again, officially winds get described from where they're from, so what this means is that towards the equator, these middle zones here, we have east winds, winds out of the east, typically in that zone. These are referred to as the trade winds. And we have west winds in the mid-latitudes, and then once more east winds near the poles. Here's a diagram of the actual standard patterns of pressure and winds on average. Yeah, land versus ocean, that makes a difference. Where do we have mountains? Other things like that, but we do see the general trends fairly straightforward there. Getting back to the water. Winds blow on the water. That gets the water moving. But not a real effective way of trying to move water. So the water only gets going a few percent of the speed the wind is moving. But also, while the wind is blowing on that water, the Earth is still spinning. And so, as a result, the water moves off sideways relative to where the wind is going. Okay, wind blows on the water, gets the water moving. As water near the surface gets moving, that's going to start to move water down underneath. But once again, it's not the most effective. We do have loss of energy from friction, all that as it goes along. So the deeper we go down, the slower things are relative to the wind. Also, the Earth is still spinning. So that direction of our currents keeps on changing due to the Coriolis. If we add this all up, we get a pattern known as an Ekman spiral. Ekman being the person that worked out the pattern mathematically. We can try to do a bit of a demonstration of this if we've got folks together for class, but for now, I'll have to just kind of describe it and go with the pictures here. Basically, the water near the surface ends up going at about a 45-degree angle. Yeah, it looks like I'm reasonably close to 45 there with my hands. relative to the wind direction. Here in the northern hemisphere, that will be to the right. In the southern hemisphere, the current is off to the left relative to the wind. Okay, go a little down. The current there is even further over to the right, more than 45, and not quite as strong. And so you keep getting a little deeper, a little weaker, and we form this shrinking spiral pattern, or Ekman spiral. Turns out, if we add up all these arrows, the net effect is that water overall is moving sideways, 90 degrees off to the side relative to the direction of the wind. Again, here in the northern hemisphere, that will be 90 degrees to the right. In the southern hemisphere, if this is our wind, it's 90 degrees to the left. Moving water sideways, if it runs to an obstacle, that water has to go somewhere, and it'll tend to go up or down, so that we may have upwelling or downwelling. So let's say we've got this water body between two areas of land in green. Our wind's going this way, we're in the northern hemisphere. Then that's going to tend to send water this way. If water is moving to the right across the screen here, that means extra water is running into the land on the right. Extra water, try to push in. We're going to tend to see sinking there, downwelling. Our other coast here to the left, water is moving away from it. But if you've ever tried, it is not easy to dig a hole in water. Water is going to slosh around, try to fill things in. So if we are moving water away from the land here, that's going to tend to promote water from deeper down rising up. So we'll tend to see upwelling along our coast here. Picturing cross-section now rather than looking down from the top. If we assume that the wind is blowing into the screen here, then the water in northern hemisphere will be tending to go off here towards the right, and running into the land will be pushed down deeper here, moving away from this side, and so deep water tends to rise there. Again, this affects the temperature and nutrient levels of the water where it's moving to as well. Again, this is happening if the wind is moving basically parallel to the direction of the coastline of the land. Why might you expect to see wind going more parallel to the land-sea boundary? And around here, land's pretty flat near the ocean. Wind can kind of blow however it wants to pretty easily. But many other coasts, like say most of the west coast of North America, we have even mountains pretty close to the ocean. And so that will tend to promote having the wind blow along the ocean rather than trying to go up and over the mountains. So having wind blowing parallel to land and thus setting up upwelling and downwelling is a common pattern. So here we go. We've got the red being the wind pattern and the black arrows showing the resulting directions of current. And you'll note a pattern both in the north and the south. we see that this tends to promote currents that are going more or less from the east towards the west. So the east side of an ocean, of course we live on land, so we tend to think of that as the west side of the continent, but east side of the ocean tends to be an area of water moving away, and so we tend to have upwelling, cooler, more nutrient-rich waters. Head over to the west side of the ocean, and that current is headed towards there, runs into the land, forced to sink down. We'll tend to have warmer, clearer, more nutrient-poor waters along the east side of a continent, west side of the ocean. Another pattern, much more smaller scale, that we see happening in the ocean is known as Langmuir circulation. Again, that's the name of the person that worked out the math pattern there. This is a roughly spiral movement of water, but it's a near horizontal spiral. And rather than being at right angles to the wind, it's close to parallel. And we get a pattern where these spirals that are next to each other are rotating in opposite directions, either like this, or else we're getting, to the extent you can see my hands, there we go, it's a little, that type of thing going on. This is set up if we have a wind that's not too strong, but it keeps blowing for a while, enough to get a pattern of response in the water going. Okay, if we have a spot where the water is going up on both sides of the spiral, then that tends to push water away from there at the surface, and floating stuff will move away from that spot. If we've got a spot where the two spirals are coming towards each other, that pushes floating stuff into the middle there. The water sinks. Floating stuff doesn't sink. And so you tend to get stuff floating on the ocean, such as foam, concentrated into these streaks if we have Langmuir circulation happening. And indeed, that's how it was first noticed. Getting these patterns of stripes of floating material on the sea surface. And some oceanographer noticed this and, why is that happening? Worked through, figured it out. When we took a look at the large-scale patterns of winds, we saw that we typically have winds blowing along from the east near the equator, from the west in the mid-latitudes, and so this tends to set up these large loops of current known as gyres. Again, winds blowing, Coriolis effect, bend stuff off sideways. Also, we got lots of land, currents run into those, can't just keep on going, so that also helps promote the currents bending into loops rather than just going all the way around the globe. Unless you're, say, between South America and Antarctica, there's not much opportunity for water to try to go all the way around. Creating these loops of current sets up patterns of either water moving apart in the currents, and if the surface water is moving out like that, deep water will rise up to replace it. And so we have upwelling where currents diverge. Yeah, like the situation plate tectonics. Stuff moving up in the mantle associated with the diverging plates. If we have currents coming together, well, that's adding extra water to a place. Extra water, that'll tend to have sinking, downwelling, where there is convergence. When we set up those loops of circulation due to the winds, again, here close to the equator, the winds are coming out of the east, mid-latitudes are coming out of the west. This tends to promote, in here in the northern hemisphere, bending to the right, so we're tending to send water in towards the middle, extra water in the middle of this gyre that will sink. Southern hemisphere bending to the left. Again, that's pushing stuff into the middle and away from the zone near the equator. Now, again, you've got complications of land and so forth. Here's a map of the actual global general patterns of currents. Water is certainly thicker than air, but still moves around pretty easily. So these currents do a lot of variation, but this is the broad typical pattern here. In the northern hemisphere, these loops are characteristically going clockwise. In the south, characteristically counterclockwise. And they're quite significant. Actually, one of the first persons to notice patterns with the currents here was Ben Franklin. Well, indirectly, it was the ship captains who noticed. Ben Franklin put the data together and realized what was going on. Basically, if ships paid attention to where these currents were and took advantage of sailing along with them, they could get across the Atlantic rather faster than if they just tried sailing back and forth without paying attention to them. And so Franklin basically was noticing what we today recognize as the Gulf Stream current, that riding along with it with your boat got you from North America to Europe quicker. Trying to sail against it would get you from Europe to North America noticeably slower. Due to these currents, we actually get extra water in places and less in others, and so there's a degree of mounding of the sea surface up and down. Now, again, water, not a great thing to try to make hail out of unless you've frozen it first. But with the consistent pushing in that's happening, we actually get tiny bulges and depressions. You'd never notice it just by going out on a boat, but it can be measured, say, using satellite or other very sensitive measurement. And also, this is over a very wide distance. Seawater is, say, well, I can't quite show a meter visible on the screen here. Well, that's close to a meter. And that difference is across many, 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 many kilometers of ocean. But water's kind of heavy. So areas with extra water will tend to have more pressure, sinking. Areas that have a little less water, lower pressure and rising water. Again, if currents are converging, that brings extra water in. We'll have something of a mound and sinking under that mound. Currents moving apart, that's taking water away. So we have a little less water. We get a bit of a depression. Water tends to flow from high pressure to low, just like wind does. So no surprise, water goes downhill. We'll tend to go away from the mounds towards the depressions. But as that water is flowing, Earth's still spinning. So we still need to take into account the Coriolis effect. And again, get into detail, where we are, how fast the current's going, affect how big an impact it has. Again, right or left, depending on which hemisphere we're in. This diagram shows the general pattern for sea surface. We have somewhat extra water, high pressure in the Caribbean, lower as we get out into the far north part of the Atlantic here. There's variation. We have steeper, and that's still a huge distance for a tiny change, but steeper along the side here, more broadly spread out as we go along here. So there's different patterns in different parts of the ocean in terms of how quickly or gradually these change. Again, that's relative terms. Quick here is still a tiny difference in elevation across a huge distance, but how huge the distance is, it does vary a little bit. Now, one pattern you might have noticed, our gyre here has currents here coming from the east towards the west, and winds coming from the east towards the west. And up in here, we've got our current coming from the west towards the east, wind coming from the west towards the east. Didn't I just tell you that current's supposed to go off 90 degrees relative to the wind? What's going on here? Did the Earth stop spinning? No, we would have noticed that. This pattern is known as geostrophic flow, and it sets up currents that end up as parallel to the wind, but it's because of different factors balancing out. We still have Coriolis going on, but other things as well. Again, as our gyre is circling, water tends to push into the middle, and so you get a low mound. This is greatly exaggerated, so you can actually see anything. You can readily imagine if this were more than 1 million times flatter, it'd look just flat. So in order to see anything, it's got extreme vertical exaggeration. As we push more water in, more extra water, gravity and pressure are pushing back down again. And it turns out that downwards gravity pressure effect and the Coriolis will eventually balance out. And that leaves the current to flow around in its loop, not obviously being bent one way or the other. Another diagram version of this, again over here, shows the wind direction and relative strength. And currents are tending to go off to the side, but we also have the flow back out from that extra water being pushed in, and those end up balancing out, and we're left with our ocean current looping around, roughly paralleling the wind directions. So it's that balance that leads to our standard pattern of geostrophic flow, not obviously showing that Coriolis deflection. Currents are different in different places. We tend to have much more narrow, deep, fast currents along the west side of an ocean, or part of an ocean, and much more broad, shallow, slower currents towards the east side. Okay. Why? Well, more generally, we have the fact that it's water flowing through water. It's not too hard to move water around, so we can easily get different shapes as the water flow moves. So that allows us to get variety here. Much trickier to try to do something like this with a river. Okay, well, what else is going on here? The Earth is spinning towards the east. So if we're moving the Earth this way, towards the right side in this picture, that will tend to spread water out to the left. And so we get this broad current here. On the other side, yep, the water is being pushed the same direction, but not very far over here, it's land. So that current can't really spread out. Instead, it gets squunched and becomes tall and deep rather than broad, narrow. Sorry, narrow depth. Broad this way, relatively shallow that way. In the middle, again, we're pushing in extra surface water, so that tends to be relatively warm and nutrient poor. Also, the current helps keep stuff washing off of the land from getting into the middle, so that extra mud and bits of decayed plant and whatnot are not getting out into the middle very much. The Sargasso Sea is the area in the North Atlantic Gyre, relatively warm water there, strong thermocline, go down underneath it. Then we have much colder water deep down, but this warm lens on top. And also the current provides a strong barrier relative to cooler water beyond. Again, water is pushing in there, so whatever's floating is going to ride with it and tend to be in the middle as well. The Sargasso Sea refers to the fact that there's a lot of sargassum seaweed in it. Sargassum is an unusual seaweed for large seaweeds in that if a piece breaks off, it'll be perfectly happy floating around, growing, living like that. Most large seaweed, if they break off from where they're attached, they'll end up dying. Sargassum, however, can happily just keep right on growing even though it's broken off and floating around. Now, of course, there are plenty of little tiny microscopic floating algae, but not many big ones. So in this particular part of the ocean, we get large patches of floating sargassum, which makes great places for little animals to live and hide and all that sort of thing. And there are a wide range of specialized animals that are living in with the sargassum. This kind of white stuff here looks like a bryozoan growing on top of the seaweed. If you look closely in the middle of the picture, you might see an eye, another eye, and what it especially doesn't want you to notice is this big gaping mouth. If some small animal gets close in front of it, it'll pop that mouth open and gulp in whatever that food item may be. This is a sargassum anglerfish. There are some sea slugs that have a very sargassum-like color pattern as well. Various things specialized for living in this setting. But other floating stuff ends up there as well, such as plastic. The equivalent area over in the North Pacific is often referred to as the Great Pacific Garbage Patch. All sorts of bits of floating plastic, other human-made junk that washes out into the ocean tends to get stuck in these places as well. And in turn, these are not good for animals. To some extent, chemicals in them can be directly harmful. Also, plastic is not food. If an animal eats it, sometimes can potentially choke it. But even if it does go on in, plastic's not doing them any good. So that's a significant problem. Now, of course, a challenge, plastic's also useful. How do we avoid doing anything that would be unduly harmful? Balance things out there. As a good example on plastics, well, of course, actually can't tell in the video version, but certainly in class, all of you wear clothes. That's a good thing. And you also wash them from time to time. That's good as well. But that also means that you've got lint going down the drain from the washer. And little bits of lint from artificial fibers like polyester or rayon or whatever like that wash down the rivers into the ocean and are potentially a problem for sea life. Whether animal tries eating it and gets some chemicals that are a problem, or just tummy full of plastic isn't giving you nutrition, it's an issue. And so there are some projects seeing if we can try to clean up some of the trash that's out there. Also, anything that we can do to both decrease how much trash we're producing and improve recycling, things like that are greatly desired. Okay, but back to the currents. Those relatively narrow currents towards the west side also are characteristically meandering, that is, bending back and forth, squiggling. The term is used also of rivers, comes from the Meander River in what is now Turkey, well known to the ancient Greeks as a very squiggly river, goes to basically the site of Ephesus, if I remember correctly. So we have the typically muddier and cooler water near the land and warm water in the middle. But that boundary is this squiggly, constantly changing current path. And so bends in that can potentially get broken off and move either inside the gyre or out from it and form rings with either warm or cold centers. So here's an example. On the left is a photo satellite highlighting infrared, which reflects the temperature. To the right is a diagram version. You can see the very warm waters of the Gulf Stream, and those bend offshore right around Cape Hatteras. So North Carolina is kind of the meeting of the colder and warmer waters there. But as we go along, you see this big bend. The kind of gappy area there is just clouds. This bend might eventually get broken off. And because of that, you could get this little patch of warm water with current circulation all around it that's drifting off into the cooler water beyond. Or you could go the other way and get a cool patch loop moving in towards the middle. So here you see diagram is we get this big squiggle in the current. Parts come close enough and it actually pinches off as its own little ring. Here's another bend in the current, and once again this becomes its own ring. Okay. Some types of ocean animals like it warm, some like it cool, and so you get different animals associated with these. Up here, there's Cape Cod, Massachusetts, typically fairly cool water. But you occasionally find a stray warm water fish or other animal turning up there because it got caught in one of these warm eddies pinching off of the Gulf Stream, moving up. Or conversely, colder water things can move into this central warm patch. So we do get some mixing exchange between the areas, but overall the current provides a barrier. Moving barrier, but a barrier. Okay, here's a good point to stop. We've looked at major features of the surface ocean currents and circulation. Wind and its main power. Pattern of the Earth's spin helps determine direction. What's going on way down in the deep? That is the question we'll leave with at this point. Okay, so deep ocean circulation next time.